Not 100% certain. Maybe 7.6? Let me see, where's your book? Is that the one with the center of mass and, yeah, centroids? Yeah, is that 7.6? All right, so 7.5 is the work, and that's just physics, and I don't feel like talking about it. And so I won't be asking you questions or assigning problems out of that. And 7.7 is also like some hydraulic stuff. So that's also physics. Yeah, fluid pressure and fluid force. So I'm sure Jimmy will probably already talk to you about that. Or not, I don't know. So I won't be. But I'll just do 7.6 because this is the fun one. And we'll get a very interesting result at the very end. That's what Owen brought up a few days ago in class. So we're actually going to make that knowledge official. But so that's what you're, as far as your exam is concerned, 7.5 through 7.4. I'm sorry, 7.1 through 7.4 and 7.6. No, 7.5. 7.7, right? Yes, but no 6.4. We didn't do 6.4. So section 7.6, the centroids and moments. So first we need to, but basically what we're going to end up doing, we want to find a center of mass of a planar, and we call it planar plate. Sometimes it's called lamina. Basically, that's exactly what it sounds to be like. If I have a piece of paper, I want to find a point, so it like balances on it, right? So that would be the center of mass. So speaking graphically, like if I have some kind of a region, so I want to find a point, let's call it x bar, y bar, and we're going to call that point center of mass. It's just a flat. So basically, we want to not think about it as a volume. So it's basically it's a pretty uniformly distributed substance of consistent density. So we're actually going to be talking about, like in physics, you talk density in terms of volume, right? Here we're going to talk about density in terms of area. We're just going to ignore the thickness of it. It's whatever amount of weight per units of area rather than units of volume. Because we don't, we're cheating when we're talking volumes, by the way, in this class. Because in order to talk about volumes, you do need to be in a three-dimensional world. We're still in a two-dimensional world, but we're talking about three-dimensional objects. So that's where all this rotation mumbo-jumbo comes from. In Calc 3, you're just going to say, hey, we have an extra axis. So the volumes are much more comfortable. So you're going to become the three-dimensional beings. So center of mass or centroid. Now, to make things a little simpler, of course, eventually we're going to start with something like this. You have some kind of a function. So whatever the, area under the curve of that function from A to B, we're going to try to, find that center of mass of centroid. So it's literally a geometric center of that region. Okay, but you kind of understand what I'm trying to talk about, as far as balancing things. I mean, we want to avoid actually talking about the mass of that thing, but we cannot do that at first because, well, that's how you find the thing, right? Things need to balance, so they have to have some kind of a mass. So I'm actually going to start playing a little games first. We're going to go to a playground, do one of those things. What do you call that? Yeah, we'll do that. What is it again? Seesaw. All right. Well, whatever you want to call that, the balancy thingy. Okay, so let's talk about that. So let's say, you know, so I'm gonna start drawing things. So let's call that point C, and this distance, let's call it x1. I don't know how much of this you want to be writing down. x2, and let's call, so here's a mass here, m1, and here's a mass here, m2. Okay, so if we go to a real playground and we find one of those seesaws and you try to play against me, for example, I might, for some of you, might be challenging to enjoy the activity of seesawing that thing where, you know, I'm sitting on one of the ends. Or, so, you know, to make that more fun, we might have to move the point where the thing is tipping about, right? Probably closer to me, maybe, depending who I'm playing with, but it's pretty safe. Because why? I mean, and try to be nice. But do you agree with that? That I like the distance from me to the point of the TP.
Way less than your big muscular self.
Right. So clearly, yes. Thank you. So we need to put some words, some verbiage here to make it a little easier to converse about. So we want to define a notion of a moment, like, and we define a moment as basically a mass times the distance to that point. Okay? So the bigger the mass, the bigger the moment, the bigger the distance, the bigger the moment. So if you shorten the distance, the bigger mass might have the same moment as the smaller mass with the bigger distance. Okay? And we basically want to get it to a point where this whole thing balances. Okay, so that C would be the center of mass of that seesawy system. Does that make sense? Okay, so I'm going to be writing some definitions down. So a moment. So given, so for this system, we're just going to start with two masses. So given two masses on a straight line like that, we say that the moment of m1 of that first mass with respect to a point C is this. So let's call it big m1 equals little m1 times x1. So is the mass times the distance. And similarly, and I'm not 100% certain that's how you spell that. Is that close enough? Nice. So the moment, so same statement only from M2. So the moment of M2 with respect to point C is M2 equals M2x2. What was that? So if C is the center of mass, then yes. So that's what I want to write. So we say, okay, that really came out messy. So we say that C is a center of mass of the system if m1 equals m2, or this holds. Okay? So, but again, like x1, this is just so you know, this is the distance. It's not necessarily a coordinate, right? I should have just probably used the d's there. But if I put it on a number line, again, we can think of this system with respect to the origin, and so the x1 and x2 would be the distances from the origin, okay? So this probably would have been better if we used these here. But anyways, so if we try to put it onto a number line, so if I actually go to a number line, and let's say this is the origin here, and I will literally say, okay, m1 is placed here, so x1 will be the distance from the origin, and let's say if I place m2 here, x2 is the distance from the origin. So somewhere again, you know, the center of mass, let's say this point C, let's label it with an x bar. So now x1 and x2 would be the actual distance from the origin as a point on the number line. That's a little easier to think about, because again, we're going to end up talking two-dimensional shapes, so we do need to define a distance with respect to the origin. So then in this case, in order for me, so let's talk about this case. What is the moment of the first mass? Well, yeah, only x bar. Let's use x bar as a, so x would be the, you know, the location. So yes, it is m1 times the distance. So let's just do it x bar minus x1, so we don't need to talk about, you know, absolute values or whatever. And the moment of the second mass would be m2. Yeah. I can do it that way, right? Yes. Okay. So basically, I want to try to find the location of x bar. I want to see, can I express x bar in terms of things that I probably know? So in order for this thing to balance, m1 has to equal to m2. So therefore, m1 x bar minus x1 equals m2 x2 minus x bar. I want to solve for x bar. Okay? I want to find that center, so solve. So this is algebra, shouldn't be too bad. m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. Right? So rearrange this equation slightly. m1 x bar plus m2 x bar equals m1 x1 plus m2 x2. Factor. And divide. So now, you know, this is just simple manipulation, right? There's nothing fancy about that. But if I think about this formula, the denominator, that's the total mass of that system, right? It's the sum of all masses. So this is the total mass while the numerator, well, it's the sum of all moments, right? M1x1 is the moment of the first mass, M2x2 is the moment of the second mass, right? So that's the sum of moments. So, yeah. Is that okay? How we, kind of driving that formula. If we move to a two-dimensional space, so this is, we're just on the one dimension. If I just do something like this, M1 here, let's do M2 here, and like M3 here, and I want to find a center of mass with respect to some line, let's say. Here's a line L. Okay, so I want to kind of balance that system with respect to that line. So I need to look at the distances again. So here's, whatever this is. So this is the distance. Let's call it D2. Here's a distance, D1. Here's distance, D3. Now, can you kind of guesstimate where the center of mass might be? Yeah, somewhere in the middle, right? Let's just call it, like here or whatever, right? Is that okay? You mean to the left like this? Are you messing with me right now, or are you? Is that okay? Okay. Well, let me ask you this question. Do you think, as far as the center of mass, with respect to that line, if I move it, if I take this point, and if I move it here, it'd still be the center of mass, right? The moments would be the same with respect to that line, right? It doesn't affect the distances, right? There is no reference in that direction, right? So anything really along this line, which is parallel to the reference line, will probably make us happy as far as locating the. So, but in order for me to really be able to pinpoint that set, I need another reference. I probably need another line. See what I mean? So I want to see the moments with respect to one line, and the line that's not necessarily parallel. Shouldn't be parallel at all to the reference line. Now, if that's the case, the one thing that's easy to do, what are the two lines that are not parallel and we like to play with? Perpendicular, and so, our little x and y axis, right? So then we can actually talk about the moments with respect to the x-axis and the moments with respect to the y-axis, and then if we can actually find a nice little point with a little more precision. Is that okay? Probably going to write a few more formulas. Right? Is that okay? What I'm talking about here? Because if I try to find the moments of this system, what would that be? It's just M1 D1 plus M2 D2 plus M3 D3, right? where d1, d2, d3 just the distance from the line. There is no other reference. So I need the reference. So anyways, so xy. Let's talk about xy systems. It's a little better. So again, I'm going to start talking about three masses. Let's say M1, M2, M3. So now I want to basically balance the moments with respect to the x and with respect to the y-axis. So here, we actually, if I think about this, I'm almost finding the center of this shape. So I want to find the moment with respect to the x and the moment with respect to the y. So, what are the distances? What is this distance right here? It's whatever the y value is, right? So this is some y1, and this is some y2, and this is some y3, right? While here, this is some x1, this is some x2, and that distance now got really messy, x3. Is that okay? So if and the center is somewhere in there, so x bar, y bar. So if I think about the moment with respect to the x-axis, and again, I want to make sure I'm labeling things correctly. Well, let me try it again. My x bar, in order to compute the x bar, man, this is not right. Yeah, go ahead. Yeah. So well, M1 contains some kind of mass still. We're putting. What is your question then? Well, what value of M1 is M1? That's not just the point. You're placing a mass at that point. Okay? So the mass is M1. And now the location of that point, the coordinates are, the x1, y1. Okay? If you have those 3 points, because eventually we're going to try to look at the region. But for now, not necessarily, not in this model. I'm just literally talking about three masses placed. Okay. Eventually, we're going to move to a uniform surface. Right now, we just have three things hanging. Okay. So this is not necessarily a geometrical center right now, because they could be different. Okay. If I make them the same, then yes, we'll be looking for a geometrical center. So right now, from what we did earlier to compute x bar, it'll just be so m1 x1 plus m2 x2 plus m3 x3 over m1 plus m2 plus m3. Okay, from the previous formula. Is that okay? Because again, if you think about this, when I'm computing the x bar, so it's the how far away from the y-axis that center of mass is located. So we're looking at the moment really around the y-axis here, right? So that's why we're looking these distances. While the y bar, well, is going to be kind of the same thing. Yeah, that's right. So again, the numerator would be the sum of all moments while the denominator is the total mass. So is that okay? How we can, I mean, we can do an example. If we just do an example of this system, let's say I'll give you, let's say, I'll give you a mass. We can actually assign values to the masses. So, 2, 3, 1, whatever the units of weight are. And we can give the locations, I don't know, 1, 2, that's the location of this one, 2, 3, 4, 1. Okay? So we can find the center of mass of that system by just following that formula. The x location would be, so we'd go, what, 2 times 1 plus 3 times 2 plus 1 times 4 over the total mass, 2 plus 3 plus 1. So what does that equal? 2. And the y bar, so you go 2 times 2 plus 3 times 3 plus 1 times 1 over same thing. What? Is it also? So it's 4 plus 9, 14, 14, 6, so yeah, 7 thirds. So this will be the location of the center of mass of that system. If I add another mass equals 7 and whatever the location I choose, I'll just have to, go 7 times 5 plus 7 times 6 will give me. And then the mass in the bottom, yeah, thank you. Whatever those are. Okay? All right, so let's talk about the actual regions. Yes, you're exactly right, because there are some summations popping up. So, but now if I actually want to talk about not a discrete number of different masses scattered in the plane, I want to talk about a region, and to make it somewhat more simplistic, of uniform depth and weight. So weight is distributed. I should be very careful when I say that. Not I mean, I can say uniformly. Do you know what I'm trying? Uniform density. Well, density should, yeah, first of all, density stays the same material. So density here is the same as density there, and the thickness is the same throughout. That's basically what I'm trying to say. So eventually what we're going to be talking about is just a object of, that's, the thickness of that object is irrelevant. That's what I'm trying to say. It's all going to be about what is the area of that object. See what I mean? That's what we're going to end up looking at. This is our way to cheat the third dimension a little bit. So it's not. Yeah, but we don't. We don't have the Z bar. You know what I mean? That's Calc 2. In Calc 3, you're going to have a whole chapter, probably, let's see, 14 maybe. We're going to get into the same story with the Z bar. Okay, so you'll be looking for a center of mass of a three-dimensional object. Okay, But now we're trying to 2D our way out of it. So here's the story. So consider, and this is we're about to start having some fun. Consider a plate with mass distributed uniformly in the region. Let's call the region R. With constant density and let's call the density, rho for density. And in this case, as I mentioned, the units here, units of density would be the units of mass to the units of area. So this is kind of a little bit different from what you use in physics, but again, we're trying to avoid the third dimension here. Okay. So here's some function, and here's that region. So we're going to try to compute, we want to find that center eventually. Now, again, from what we agreed, the x bar is the sum of moments, so I can actually write it like this, would be the summation of mi xi as I goes from 1 to whatever we like, n, over just the total mass. So here, let's talk about total mass. I mean, how do you find a total mass here? I mean, that's actually an easy question. But if we, yeah, I mean, it's just going to be, the density of the thing is just area times the density, right? We're going to eventually end up with this, rho times the area. But the hard part is to figure out the moments. Okay, so moments around the y-axis and the moments around the x-axis. That's going to be a little trickier. So what we're going to do, we're just going to try to figure out the moments of which one of those little bars. I mean, we're going to take this thing and slice it into something that's easy to deal with. Okay, so let's just focus on one of those little rectangles. Okay, and just think about, again, think about the center of mass of that thing. How would we find the center of mass with I mean, with respect to the x-axis, that's almost simple, right? If you want to find the y bar of that little segment, I mean, if you think about this, this is a uniformly distributed weight. What do you think the center of mass on the y is going to be, the y coordinate? Halfway, right? There's going to be half the distance, right? So it is 1/2 the value of your function at whatever your x sub I is. Right?
So then you get to average all of your y values.
Well, eventually, again, because the idea is to find the center of mass of which one of those um, objects, and then the formula suggests to add them up. Now, how do we add things up at this point? I mean, we're going to end up integrating, but if you think about this, I mean, what is the mass? I mean, the mass is the row times the area, right? Well, what is the area of this box? I mean, let's call this side delta x. What? Yeah, so f of whatever xi is times delta x, right? So this is the mass, and then times the x, how far away is it from the y-axis? So times xi. While here, I mean, eventually we're going to get to this point, but the mass is just the row times the area, right? And the area is, again, f of x delta x, not delta x, dx, f of xi. So this is where we're getting to here, is the summation as I goes from 1 to n, rho x sub I, f of x sub I, delta x, over the summation as I goes from 1 to n, rho f of x sub I, dx. Yeah. Is that okay? Now, rho is a constant, so it's just going to cancel out. Rho becomes irrelevant in this case. So we're getting to the point, rho's cancel, so the x bar is given by I from 1 to n, x sub I, f of x sub I, delta x over the summation from 1 to n, f of x sub I, dx. Is that all right? Well, the density. So rho is a constant. So if we agreed on that, we can, from the summation, we can factor the rows out. They'll cancel. Okay. Yeah. Now let's see how we can get the y bar. We started doing that. So the y bar, there will be the moments around the x-axis. So the numerator, denominator will still be the sum of all masses. So we're going to end up with the same result as with that one. Now the numerator is a little trickier. No, it will still be delta x. We still look at it that way. We're still looking at the same shape. We're not going to start cutting the other way, right? So the delta is whatever, along which axis we do our slices, right? So we're still looking at this slice. So the mass of this thing will still be the same, right? So the denominator will come out to be the same. We're going to have that rho f of x sub I delta x. Now, the numerator, And I had it earlier. Um, it's a very funky result, but we can reason through it. Yeah, and never mind. So, so what do we need? We need the mass and the distance, right? This is what we need. Now, again, what is the, because remember, this is, the numerator should be this, m sub I, y sub I, as I goes from 1 to n. Now, the mass is, again, the area times the density, so we can get the mass that way, so it's rho times the area, so it's f of x sub I delta x. And as I mentioned earlier, now the distance that the center of mass of each of those segment has from the x-axis is exactly halfway, right? That's what we agreed on. So this is the distance, so it becomes 1/2 f of x sub I as I goes from 1 to n. So as before, rows cancel, and I goes from 1 to n, 1/2 f of x sub I squared delta x over rows cancel. This is where the formula comes from. This is one of those moments where you fix your car and you don't know why, right? That's what we talked about last time. Now what's going to happen with this? We're going to take the limit, right? We're going to shrink delta x, right? We want delta x to virtually go to 0. So this whole thing is going to stretch out into integrals. So to find the center of mass, so the x bar becomes the integral from a to b, whatever the ab's are, ab of, what do we get? X f of x dx, while the denominator is just an integral from a to b f of x dx, right? Now what is this denominator again? It's just the area under the curve, right? This is the calc 1 thing. So you can actually think of this formula as 1 over a times the integral from a to b x f of x dx. Okay? So this is how you can find the x coordinate of that central region, of that centroid. 1 over a, where the area, where a is the area under the curve, and whatever that integral is. While the y bar, so if we convert all that, so we get 1/2 f of x squared dx over the integral from a to b f of x dx. So again, denominator is the area, so the whole thing is 1 over a, the integral from a to b, 1/2 f of x squared dx. Yeah, there are no square roots, right? But of course we can make it a little more interesting. But anyway, so this is the derivation of these formulas. You don't need to have these formulas memorized because they're not that intuitive. Like with other ones, you can always kind of reason to it. On the exam, I'll give you those, so don't worry about them. Just need to use them. So let's do an example. I want to find, so find the center of mass of the plate stated below, I guess. I'm just going to draw a picture and we'll know what we're talking about. So it's basically it's bounded by the square root of x, and just go from 0 to 1. So I want to find x bar, y bar. So when you do these problems, the first thing you should do is always find the area of that region, because that area is in both formulas, right? You need to know what the total area is. So that's the first thing you do. Just let's compute A first. So that's simple. That's calc 1. A is the integral from 0 to 1 square root of x dx. So the antiderivative of square root of x is 3/2 x, no, it's 2/3. That's big. So it's x to the 3/2 and then 2/3 from 0 to 1. So the area is, yeah, so 2/3. So to find x bar, I just need to go 1 over a, an integral from 0 to 1, x times f of x dx, right? Is that our formula? So 1 over a is 2/3, so this whole thing becomes 3/2, an integral from 0 to 1. This is x to the 3/2 already. So 3/2 times what? 2/5 times x to the 5/2 from 0 to 1. So yes, 2's cancel, plug in 1, you get 3/5. Now y bar, it's 1 over a, the integral from 0 to 1 of 1/2 times the function squared dx. So this is 3/2. I can pull 1/2 out, and I'm just integrating, looks like x dx, right? When you square the square root. So this becomes 3/4 times x squared over 2 from 0 to 1. 3/8. So the center of mass, or centroid basically of this region, is 3/5, 3/8. How's this? Is this okay? The example isn't too bad. I had a bad one somewhere.
I have kind of a related question.
Yeah.
Square root of any non-square number irrational.
is a square root of any number that's not a perfect square irrational? Um,
Give me one that is. Square one. No, square root one.
yeah, yeah, it's irrational. So the square root of any number that's not a perfect square is going to be irrational.
Any integer. Because you was just given.
Well, yeah, any integer. That's what we're talking about, right? I mean, the
That's fine. That's right. You took it to rational.
yes.
Yeah, square roots of 5 is
I mean, if it's even, then you're always going to end up with a square root of 2 of sorts. So that makes it rational. And if it's odd, you're going to end up with probably a prime somewhere in there anyway. So odd one. So why? Completely unrelated.
Yeah.
Okay.
I was just wondering, 'cause it seems like a pretty nice formula for stuff that's going to be crazy rational.
Well, but we chose from 0. I mean, if we change it from, from 0 to 5, then it's probably going to come out ugly. But if we change it from 0 to 4 or from 0 to 9, they're all going to come out pretty. You're not going to have any, right?
0
Yeah. From perfect square to perfect square. 4 to 9 is going to come out probably pretty. Okay. Now a little addition to the formula, region bounded by curves. By, let's say, 2 curves. So let's say if I have a function f and a function g. And just to make things simpler, let's just say on that interval from a to b, f stays greater than or equal to g at all times. So we're looking for that. So again, if I just look at this one little piece, from what we discussed earlier, I'm not even going to bother with the summation. I just go straight for the integrals. Is that okay? I mean, I'll talk about what's happening in there, but so denominator will be the total area, right? So what is the area of a region bounded by 2 curves, between 2 curves? It's just going to be the integral from a to b, f of x minus g of x, right? That's our section 7.1. So that's the easy part, from a to b, f of x minus g of x. Now in the numerator, so again, it's the mass times the distance, right? So the distance from the y-axis is just whatever the x is. Now the mass was basically, it's the rho times the area, right? The rho will cancel. Now the area of this region is the width, which is delta x or dx, times the height, which is f minus g, right? So it's going to be f of x minus g of x dx. So eventually we still end up with 1 over the area of the region times the integral from a to b x and the difference in there. So it's f minus g. Now, the y bar, again, the denominator will stay the same. Denominator is the total area. So again, it's f minus g. But the numerator now, again, the numerator is the mass times the distance, right? The y values. So the mass, again, will be the area times the density. So the area is, again, the difference between two functions times the width, the delta x, so it becomes dx. So this is the area right here. Now the mass, I mean, not the mass, the distance from the x-axis. So again, this has to be in the middle, right? If it's a uniform thing, it has to be in the middle of that little. Well, yeah, but I mean, how do you find that middle in terms of f and g? I mean, yeah, you can take 1/2 out, but is it f minus? Yeah, you're going to average the two heights, basically. That's what you're doing. It's going to have a plus, so it's 1/2. I don't have places for x's, f plus g. You're going to hold this against me? Okay, sorry about that. So you have to make sure they're of x's. Now f plus g, f minus g, that's the perfect difference of squares. So this becomes 1 over the area, and then the integral from a to b, 1/2, and then it's actually f of x squared minus g of x squared dx, the difference of squares form, f plus g, f minus g. So the difference of squares. Okay, so here's the formulas for the region bounded in between. Okay. So let's try this. I don't know if we're going to finish this one. It's going to get a little messy. So find the centroid of the region, and the region is this. It's bounded by these two curves, -1, +1. So I have an upside down parabola, y equals 2 minus 2x squared, and then I have a semicircle in here, and that's y equals the square root of 1 minus x squared. So I want to do this region. How can what be? Right? So it's not negative, right? It's okay. Now one of the coordinates is very easy. What do you think where's the point going to be located? I mean, where's the point going to be? It's going to be along the y-axis, right? I mean, this is symmetry, so it has to bounce along the y-axis. So what is x bar? 0. So we already need to find the y bar, really, right? I mean, we do have to find the area of this region, right? And we can kind of cheat, because, I mean, we do know the area of this, don't we? The area of half a circle of radius 1. Yeah, and r is 1, so it's pi over 2, right? So the area that we're looking for is really going to be the integral, double the integral from 0 to 1 of 2 minus 2x squared dx minus pi over 2. Is that okay? Is the area under the parabola minus... yeah, we have time to do this one. So it's 2x minus 2/3 x cubed, is that correct? From 0 to 1 minus pi over 2. So what do we get? So it's 2 times 2 minus 2/3. So what's 2 minus 2/3? 4/3, so it's 8/3 minus pi over 2. Whatever that is. That's the area, so 1 over that is going to go in front of our integral. So the x-coordinate, I'm sorry, x-coordinate, we found that at 0. Y-coordinate, so it's going to be 1 over the area. I mean, I should probably do the thing. So what is that? So it's 16 minus 3 pi. Is that right? If you do the common denominator, multiply first, so it's 16 minus 3 pi over 6. Is that right? So 6 over 16 minus 3 pi, and then the integral, and again we can do the, technically I have to go from -1 to 1. Everything is even, so double this, go from 0 to 1. And then remember, we need to take 2 minus 2x squared minus the square root of 1 minus x squared dx. The LCD, 3 and 2. I mean, because it's just easy to flip it if you LCD away to that. Yeah, there's still 1/2, you're right. So there's still 1/2, so it cancels with the 2. Yeah, you're right. So overall it's going to be 6 over 16 minus 3 pi and blah. Right? Bloody x. Right? Bloody x. Right? And you can compute the rest, right? The square root goes away, it becomes a polynomial, so it's a fun integral, right? You know, you can do it later. I want to do another example that's a little uglier. So looking at the region, and it's bounded by y equals x, y equals 0, y equals 1 over x, and x equals 2. So graphing these things, not necessary, but certainly helps. So 1 over x, y equals x, y equals 0, so there's the x-axis, and x equals 2, so this is 1, 1, so 2 somewhere here. So this is the region. Yeah, you're going to end up doing 2 integrals, right? Because, I mean, to do the integral under the curve, right, to compute the area, you'll have to go an integral from 0 to 1 of x dx plus the integral from 1 to 2, 1 over x dx, right? So x squared over 2 evaluated from 0 to 1 plus natural log of x evaluated from 1 to 2. So we're ending up with 1/2 minus 0 plus ln of 2 minus 0. Is that okay? I mean, the integrals are, so what is it? 2, 1 plus 2 ln of 2. So it's 1 plus ln of 4 over 2. I think it's cute. So we can do that. So now let's talk about this thing. I mean, is it still, can we still split it into two? Because again, if we understand this formula, I mean, the formula says integrate from, you know, from 0 to 2x times whatever our function is. And our function is a piecewise function, we can think about it that way. So it's from 0 to 1, it's one function. From 1 to 2, it's another function. So yes, we can go ahead and split this up. So this becomes 1 over, so the reciprocal of that, so that's 2 over 1 plus ln of 4. And then it's the integral from 0 to 1 x times the function, which is x, dx, plus the integral from 1 to 2 x times the function, that's 1 over x dx. Okay? So let's see. So the first integral is just x squared, so it becomes x cubed over 3, evaluated from 0 to 1, plus, so yeah, x is canceled, so it's just dx, the antiderivative is x, evaluated from 1 to 2. What? Oh, I have no, I'm not there yet, but looks like 4/3. So that becomes 1/3 minus 0 plus 2 minus 1, so it's plus 1. So yes, it is 2 over 1 plus ln of 4 times 4/3. Whatever that is. I think I have it. I got 1.12 or so. Is that? Is that okay? Okay. Y bar. So again, we're going to end up with two integrals. So it's the area. So it's 1 over the area, 1 plus ln of 4 times. We can pull the 1/2 out. And then it's going to be the integral from 0 to 1, x squared dx, plus the integral from 1 to 2, 1 over x squared dx. So over here, 2's cancel. We end up with 1 over 1 plus ln of 4. And then it's x cubed over 3, evaluated from 0 to 1, plus, well, what is this going to be? Negative 1 over x, right? So it's negative 1 over x, evaluated from 1 to 2. So 1/3 minus 1/2 plus 1. So it's 1/3 plus 1/2. So that's 5/6. Is that right? So it's 5 over 6 times 1 plus ln of 4. Whatever that equals to. 0.35. So the How is that? So now let me ask you this question. What if for whatever psychotic reasons, I'm going to ask you to rotate this region
Mass, or the center of mass on the surface.
No, because that would probably be the origin if I rotate around the y-axis, let's say. I mean, the axis of rotation would be the center of mass of the volume, wouldn't it? Let's not. Let's rotate it, which would be nasty. Let's rotate around the y-axis. I mean, either one of those would be, yeah, the y-axis would be a little nastier. Can I ask you to do that? Can you find the volume of the region, this region, rotated around the y-axis? Yeah, I can. How would you go about doing that? I mean, you have two options. You can do the disk method, or you can do the shell method. Now, if you do the disk, so you rotate around the y, so you're slicing that way, right? Now, if you go the shell, so you slice it that way, right? So the shell, you're going to end up with two integrals, right? You'll produce the answer. Do you agree with that? Let's do it really fast. I'm going to keep you late today. Feels like, I don't know, Friday, what else are you going to do? So, well, you have lunch till 1:15. That's, or if you don't eat here, then I really don't care when you eat lunch. So let's do that. Let's rotate around the y-axis, and we're going to find the, oh, it's all right, believe me. The things I said in my pre-calc, on Wednesday, should be investigated heavily. So if we rotate around the y-axis, so what is it going to be? So let's use the shell method. It'll be a little more humane, right? So it's going to be 2 pi, you're going to factor the 2 pi. So it's going to be the integral from 0 to 1. First, the heights are given by x, right? And the radius is given by x. So it's x times x dx plus the integral from 1 to 2. What are we getting? X times 1 over x. Is that right? That looks a little familiar. We already computed that. But it's 2 pi times, we saw that integral already. Actually, it's working out faster than I thought it would. Here's that, no. Here's that integral, right? X, x1 over x. So what did that parenthesis come out to be? 4/3, right? So it's 8 pi over 3. This is fun. Anyways, so there's this little theorem, there's this little result, which in this case would be redundant because actually the computation wasn't that bad to compute the volume this way. But there's the theorem. It's called theorem of Pappus. Okay? That tells us that we can find the volume of revolution of a region. Let's say if you have a region R, and let's say if we rotate that region let's say around the y-axis, the volume here would be the actual area of the region times the distance traveled by the center of that region. Now, let's say if this is the center, x bar, y bar. So if you rotate that way, the y doesn't change, right? The only thing that really travels is the x bar. So 2 pi x bar. So this is what Owen was asking. Remember when you asked, like, why is that not working when I take the area and multiply by 2 pi? And I was telling you have to be careful. It depends where that region is. So this is what you were, the only thing you were missing is the distance of that center. Or vice versa. If you rotate that way, it just times the y bar.
So you could, as long as you know the center.
Yeah, it's like if you know the center and the area, just go boom. In this case, it's really an overkill, but check this out. Let's just do this really fast. This is the area of the region, right? 1 over, that thing. Oh, come on. Where do you have to go? Right? It's this. Right? This is the area. And this is the x coordinate, right? I mean, this is redundant, but if you multiply this by that, the whole ugly part cancels. You're left with 4/3 times 2 pi. So 8 pi over 3, right? Can't. Need calc 3. Cannot prove it yet. I need calc 3. I really need to appreciate the third dimension to prove that. Cannot prove that. Calc 3. You're going to have you'll revisit everything that we're doing right now, you'll revisit in calc 3, and you'll be able to put a little bit of precision. But yes, I cannot prove that yet. We need calc 3. But that's a fun little theorem. So it's the area of the region times whatever the center travels. Okay? So that might make it easier if you start rotating around the slant axis. All we have to figure out.
What was the